See that? So now you got 2 times 3 equals 6. 3 times 3 equals 6. 5 times 6, 3 times 3 equals 9. 5 times 6 equals 30. I don't know what they snuck them in there. Wow, they're giving you a lot all off the bat.
What did you do?
She's
Not
Okay, so in case you didn't know already, now you know how to multiply whole numbers together. Okay, just arrange some dots into groups of the right size and then count them. You got that? Yeah, I think you do. Okay, the factor tree we showed for 30 wasn't grown out all the way. You could tell that right off, huh? It wasn't grown out. Here is the biggest factor tree we get by combining 2 of the factor trees shown in the previous page. What's Mommy doing? What's she doing over there? She trying to cause trouble? She causing trouble? Tell her to leave us alone. We're reading. Okay, now pay attention. Look over here. You got to pay attention. We're studying. There's going to be a test on this later. Okay, so 2 times 3 is 6. 5 times 6 is 30. See? The orange and yellow dots each show how we can arrange 30 dots in a way that reflects the factor tree we have drawn for 30. See, there's the orange dots. There's 6 group of 5. 5 times 6 is 30. In the orange case, we've made a 2 by 3 grid of groups of 5 dots. See, there's two groups by 3 groups. So it's 2 times 3, oh, you're multiplying 5. You got that? So there's 5, 10, 15, 20, 25, 30. In the yellow case, you have 5 groups of dots, each arranged in a grid 2 by 3. Very interesting, isn't it? Okay, now, pay attention, Miles. We're never going to get through this if we don't start paying attention. You may wonder if the factor tree we drew for 30 really is all the way grown out. After all, 1 times 2 equals 2, and 1 times 3 equals 3, and 1 times 5 equals 5. See that? The problem with allowing 1s in the factor tree is that it makes it impossible for the trees to grow forever. See? You looking at that? It says the picture looks nice, but the extra branches make it more complicated and don't tell us anything new. So we don't allow 1s in the factor trees. They're not allowed. No 1s. You're probably wondering why. But they just told us. It makes it more complicated, and it doesn't tell us anything new. That's why. It's simple as that. Okay. The rules don't mean that you can't draw the crazy kind of tree from the last page. It all depends on the numbers you choose. With the right numbers, you can follow the rules and draw some crazy trees. Two times 2, 4. 2 times 2 is 4. 2 times 2 is 4. 2 times 2 is 4, huh? 4 times 4, 16. 16 times 16 is 256. 256 times 256 is 65,536. God bless you. See? That's pretty easy. There's nothing to it. He's so quiet. How come he's so quiet?
He loves it. He likes the book.
He likes being read to.
Yeah. And so now we got 2 times 5 equals 10. 10 times 10 equals 100. 10 times 100 equals 1,000. 10 times 1,000 equals 10,000. 10 times 10,000 equals 100,000. 10 times 100,000 equals 1,000,000. 1 solid million numbers. I thought this was only going to go up to 100. The first 100 numbers and their characters. They're already going out of the boundaries here. I mean, I know you're a smart little boy, but... Okay, now here comes the part you got to remember. The numbers at the top of the fully grown factor tree are called primes. Primes. Can you say primes? Try. Primes.
He's very engaged.
I'm losing them. The numbers at the bottom of the fully grown factor tree are called composites. Those are composites. Got that? Okay. A number usually has different factor trees. A number usually has many different factor trees. But the primes that appear at the top of these different trees are all the same, at least when they are listed in order. 2 times 3 is 6. 2 times 5 is 10. 6 times 10 is 60. See how that works? Comes out so nicely. 2 times 5 is 10. 10 times 3 is 30. 2 times 3 is 60. These trees all tell us that 60 equals 2 times 2 times 3 times 5. Oh, Miles. Starting to lose me. 2 times 2 times 3 times 5. Let's see. What are we doing? Let's see. 2 times 2 times 3 times 5. 2 times 2 times 2. We're going to have to draw them all out, and we'll get a little pad and paper and draw all these out so we'll understand them better. We need to see all the dots, and then we know what we're doing. Put another way, a whole number greater than 1 is called composite if you can arrange that number of dots into a grid having more than 1 row and more than 1 column. Otherwise, it's a prime. That's pretty simple. Huh.
Seems straightforward.
Yeah. So here's the column, 6 dots. 3 columns and 2 rows. They're there. So that's a composite. That's not a prime. See? It's a grid. Now don't get sleepy on me. We've got a lot to cover yet. Okay. So 1 is a prime number. 2 is a prime number, 3 is a prime number, but not 4, because we can make a 2 by 2 grid out of it. So that's a prime number. No, that's a composite number. So 5 is a prime number, but not 6. 6 is a composite, because you can make a 2 by 3 grid. See, look at, come on, look at. 1, 2, 3, 1, 2. Okay. I know, it's getting hard on me. Okay, that's enough for today. We'll work on some more tomorrow.
We got enough of that. All right.
That's enough for today.